Assalamu alaikum. Are you able to hear me, students?
Yes, doctor, we can.
Okay, good. Okay, Assalamu alaikum. This is Dr. Muhammad Umar Siddiqui. And inshallah, this semester I will be teaching you Dynamics ENG 311, which is a 2 credit hour course for your group. For females, there are 2 groups. One group will be with me, another group will be with Dr. Muhammad Salim. Dr. Muhammad Salim group would be on Thursday, inshallah, and my group will be on Tuesday from 6 to 8. Okay, let me introduce myself a bit. I'm Dr. Muhammad Umar Siddiqui, and I'm a faculty in Mechanical and Energy Engineering Department. I have been teaching this course for quite a long time. Maybe this is like the 7th or 8th time I'm teaching this course. Previously, there was a time when I used to teach this course to both male and females together. For now, since energy department has started, so just a minute, let me send a link. Just 1 minute, huh? Okay, so now this semester, inshallah, I will be teaching this course only to one group of the females, and uh, I have other courses from the energy department, which inshallah I will be teaching. So let's discuss a little about this course initially. This course is a 2 credit hour course, and the prerequisite of this course is statics. You already know statics. You might have already passed statics since you are already entered into this. Okay, let me discuss a little about this course itself initially. Uh, this course, Dynamics, is a branch of engineering mechanics. So normally what happens is that we have engineering mechanics, and engineering mechanics is a course where we deal with how the objects are going to behave under the application of forces. Okay, when the objects are stationary, we subcategorize it as one course, and it is known as statics. And this is the course that you have already covered. So in statics, you studied the behavior of objects under the application of forces, but when the objects remain stationary. This course is a little different from the previous course in the sense that here we are going to study the behavior of objects under the application of force, but only when the objects are in motion. So this course is a continuation of statics. So all the concepts of statics which you studied before could be considered as a prerequisite. I mean, equilibrium of forces, balance of forces. How do we study uh, the diagrams? Okay, all these things are the which you studied in statics will be equally applied in this course, dynamics. So if you are weak in statics, it's going to give uh, some difficulty for you in understanding this course itself, because this course is, you can consider it as a continuation of statics. In statics, you studied the book of R.C. Hibbeler, if I'm not wrong. Which book did you study from R.C. Hibbeler or any other book?
Yes, it was
It was R.C. Hibbeler, I hope so.
Hibbeler. Yeah.
So here in this course, you are also going to study R.C. Hibbeler, and the reason to continue with R.C. Hibbeler within the college is that we need to continue uh, with the conventions of the book. So if the author is same, the conventions of the book remains the same. So in the book of statics, R.C. Hibbeler, probably you studied from chapter number 1 to chapter number 11. And since this is a continuation of this book, R.C. Hibbeler, so we are going to have from chapter number 12 onward, chapters will be there in the book. So if you open the book, you will not find from chapter number 1 to 11 in the book. The first chapter is chapter number 12. Okay, just give me a minute. So so let's discuss about the material in the book. When we talk about dynamics, it is comparatively, although statics is the background of this course, but it is comparatively more difficult than the course of statics, and the student find it more difficult to really grasp the concept. Now, the main reason behind it is that in statics, everything was stationary. When you are solving problem in book, or when you are solving problem on paper, when you're looking at the problem, everything is stationary and you can see everything is stationary. However, in case of dynamics, uh, you are solving the problems on paper or you're looking the solution in the book, but in reality it is dynamics, and the objects are in motion but you cannot see the motion, and this is where the difficulty comes. Um in the course of dynamics, you have to imagine the motion. You have to have an understanding how the motion will be and how the object is going to react under the effect of that motion. And many students face difficulty here that they are not able to actually visualize the motion itself, and as a result they are not really able to understand the problem itself. So this is one big problem in understanding this course compared to statics. In statics everything was stationary, so not a big issue. Here everything is in motion, but you cannot see the motion. You have to imagine it. You need to have a sense of visualization of the motion. So if you lack that sense of visualization, you will find it difficult to really focus over the problem or understand how the problem is going to behave. So this is one big difficulty. The other thing is that the the application of this course is so vast that it is applied in almost each and every field of life. And so sometimes it becomes even difficult to really understand the scenario where this where the laws of dynamics are going to be applied. So understanding the laws of dynamics is is one problem, but understanding the scenario where it is applied is another problem itself. So sometimes it becomes really difficult to correlate the two things together. However, anyways, I will try, inshallah, in this course as much as possible to keep things simple and make it as understandable as possible for you guys. So let's discuss a little about the structure of this course. This dynamic course which we are going to study from R.C. Hibbeler. It has about from chapter number 12 till chapter number 20. It has about like 9 or 10 chapters within the book, depending upon which edition you are using. Edition to edition, there is not much difference. The major difference is only in some of the numerical problems. Uh, they change the numbers sometimes, or sometimes the formulas. Otherwise, the concept remains the same, and there is no change in the concept throughout. So we have from chapter number 12 till chapter number 20. Now, when we talk about dynamics, so we study dynamics into two different parts. One is kinematics. As you see here, this is kinematics, and the other is kinetics. So what is kinematics? When we talk about kinematics, what we mean is that study of the motion itself. So when we say about the motion, we really mean the velocity, acceleration, how is the object speeding up or slowing down, and what is the time taken in doing that. So these are the kinematics. Just dealing with the motion itself without taking into consideration what are the causes of the motion. So we do not consider the effect of force. We do not consider what are the forces which are causing this motion. So forces are of no concern for us when we are studying kinematics. So kinematics is a study of the motion itself. Then after studying kinematics, we move towards the kinetics. And in kinetics, we study the forces which are causing the motion. So we study the complete picture. So this is kinetics. So in this book, when we study dynamics, so you will initially study kinematics, and then you're going to study the kinetics. Now, studying kinetics, it has, again, 3 sub-branches. There are multiple ways. These sub-branches are basically different possibilities or different options of studying kinetics. You can study kinetics by using force acceleration method. This is one method. You can study kinetics using work and energy method. This is another method, and they are alternative. You can use work and energy method, or you can use force and acceleration method, and both methods are going to give you the same answers. And we are going to see when we are going to continue with our lectures, you will find out that yes, we will solve some problems by using both methodologies. Then we have another methodology, which is the impulse and momentum methodology. And we can study kinetics using impulse and momentum methodology as well. So there are three different methodologies of solving problems: force acceleration method, work energy method, impulse momentum method. Okay, and so if we study all the three possibilities, all the three methods, then we can study the kinetics in detail. So basically, when we have to study dynamics, so dynamics is a combination of kinematics and kinetics in totality. Okay, so how the book is defined, how the book is divided or subcategorized is that initially, when we have to study the dynamics, we study the dynamics for a particle. Now there is another concept here. What is the difference between particle and a solid body? Okay, so particle is anything which is like a dot. So what are the characteristics of a dot? A dot is something which has no shape, no size. Okay, uh, so a dot has no shape, no size. But when we say something as a solid body, so solid body has a specific shape, it has a specific size. What effect it will have over the study of dynamics? When we consider it something as a particle, since it has no shape, no size, so the rotation factor of that particle does not matter. Rotation of the particle is not going to affect the problem because the particle is a dot. However, when we consider something as a solid body, then the rotation factor cannot be ignored because now this body has a specific shape, it has a specific size, and so the body can rotate, and the rotation of the body can affect the dynamics of the problem. So the problem actually becomes more complicated when we consider a body as a solid body. However, it becomes a little less complicated when we consider it as a particle. All other laws of dynamics are equally applicable for both particles as well as solid body. Okay, so how the book is categorized? Initially, what we do is that we try to understand the simple stuff. And simple stuff means what we do is that we try to study the dynamics of particle. All other laws of dynamics will be there and we are going to study them, but only the factor of rotation of particle will be ignored because particle has no shape, no size. So the rotation of particle does not matter. So we are going to ignore the rotation of particles, okay, and thus we are going to study the dynamics initially for particles. So when we study the dynamics for particles, so chapter number 12 will be the kinematics, study of the motion of particles itself. Then chapter number 13, 14, 15 will be the kinetics of particles. So by force acceleration method, chapter 13 by work energy method, chapter 14 by impulse momentum method, chapter 15. So from chapter number 12 to 15, when you have studied, so you have actually studied the complete laws of dynamics, just ignoring one factor, which is the size of the body, that means the rotation factor on the body. Just ignoring that, you have studied complete dynamics. From chapter number 16 onward, what we do is that now we complicate the problem a little. Since we have understood the basic laws of dynamics, now what we are going to do is that we are going to consider it for solid body instead of particles. When we consider it for solid body, now the rotation factor will be there in the analysis. So the problems will become a little more complicated with the same methodology as you applied for particles. Okay, so in the same way, initially, we are going to study the kinematics of solid body, which is going to be chapter 16. Then chapter number 17, 18, 19 are the kinetics of the solid body, where 17 is by using the force acceleration method, 18 is by using the work energy method, and 19 is by using the impulse momentum method. After that, chapter 19, then you have chapter number 20, which is actually a little about vibration. And this is also part of the course. But normally this course itself, if we start covering it from chapter number 12 onwards, it becomes way too much heavy for the students to cover. So normally we do not even have time to cover chapter number 19. We normally start from chapter number 12 and almost end up at chapter number 18. And even chapter number 19 is really hardly covered. So we normally put chapter number 19 and 20 for the self-study purposes. However, in the classes, we are going to cover mostly from chapter number 12 to chapter number 18. So anyways, this was just a brief about this course. This course is basically branch of engineering mechanics. One branch you already studied, statics, when you study the effect of forces over over the bodies when the body is stationary. That was statics. And this is in continuation to statics. That's why starting from chapter number 12. And here we are going to study the effect of forces on the body when the bodies are in motion. And this is one of the reasons that this course is a bit more complicated than statics, because there is motion and you have to visualize the motion, but you cannot see the motion yourself. And since you cannot see the motion, sometimes it becomes more difficult to actually visualize it and to analyze how the forces are going to affect the motion of the body. But anyways, this was about the introduction to dynamics itself. Since I'm giving an online lecture and I do not know whether you are able to hear me properly or not, I don't know whether you are understanding, you're actually with me or not. So let me give it a break here and let me ask from you. Are you able to hear me properly? Are you able to understand whatever I'm saying? Good. Is my English clear? Okay, good. Okay, that was about the journal introduction to dynamics. Now let's move towards. Okay, I need to know first. In this group, is there any class leader or for the group? Who Najwa and Reem. Okay. Okay. So anyways, I will be uploading, inshallah, all the material over the Blackboard. However, in case if I need to communicate with the students or I need, or the students want to discuss anything with me, it is better that the point of discussion should be only, should only be the class leader. Okay. So I will respond the emails of class leader only, or I will send email to class leader only. And I will presume that the class leader will actually transfer my message to the whole class or transfer the message of the class to me. Okay, let's discuss a little about the course contents, the syllabus. Okay, uh, the book I have.
Doctor,
Yes.
can we take a break for 10 minutes because most of the girls want to pray?
Yeah, I also want to pray. Actually, this is good. Okay, about that, I also want to ask. Look, the class timing is from 6 to 8. Okay, so are you guys free before 6 or not? Because if we start the class, let's say 15 minutes before 6, like 5:45, then during that time, when the Maghrib prayer comes, so we can take a break of, let's say, half an hour, and then after that we continue back. So that will be better. Right now I also need to pray. So let me know if it is possible that, because even after this class, directly I have another class from after your class ends at 8 o'clock, then from 8 to 9, I have another class. So if you have time before 6 o'clock, so we might be starting like 15 minutes before 6, that would be much better. We can have time for the prayer. If not, it's okay. We are going to continue like that. Okay, let's have a break of 10 minutes or 10 to 15 minutes. Let's pray and then we'll be back.
Doctor? I think you can start now.
Okay, let's start back. Okay, let's discuss about the course schedule and distribution of marks. So we are talking about 15 weeks from week 1 to week 15. Okay, so we are starting right now here on September 1. Next class will be September 8, and so on and so forth, from September to October, November, December. Okay, our coverage will be like that. In the first 2 weeks, we will continue with chapter 12. We, inshallah, will finish that. Then third week, chapter number 15. Fourth, fifth, chapter 14. Then sixth, seventh, chapter 15. Eight and nine, chapter 16. Then on week 10, most probably we will have our midterm exam. So no lecture will be there on week 10. Week 11, week 12, chapter 17, week 13, chapter 18, week 14, chapter 18, week 15 will be the revision. So anyways, this is how our study is going to take place from chapter number 12 to chapter number 18 throughout the semester. Corresponding to each chapter, you will have homework problems. So from chapter number, you see here, it's already mentioned. From chapter number 12, you will have homework problems. Then from chapter 13, chapter 14, 15, 16, 17, 18. So they're like homeworks from homework 1, 2, 3, 4, 5, 6, 7. So you have 7 homeworks. Corresponding to 7 homeworks, they are mentioned at what are the deadline for the submission of homeworks. So you'll have homework 1 should be submitted in week 3. Then homework 2 like this, week 5. Homework 3, week 7. Then homework 4, homework 5, homework 6, homework 7. You will have for homeworks, 15% will be the marks for the homework. 15% will be for the midterm. You will have 3 quizzes. One quiz will be from chapter number 12 and 13. The second quiz will be from chapter number 14 and 15. The third quiz will be from chapter number 17. The midterm will be from chapter number 12 to chapter number 16. So the quiz 1 will be in the 5th week, quiz 2 will be on the 9th week, quiz 3 will be on the 14th week. Most probably all the quizzes will be online, and as per my knowledge, the midterm exam you have to come to the university and give a paper-based exam. Similarly for the final exam. Final will be 40%, quizzes will be 30%, 3 quizzes means 10% each quiz. 15% will be for the midterm, 15% will be for the homeworks. That makes a total of 100%. So this is how the course schedule and marks distribution will be. The topics are already mentioned here. Chapter number 12, 13, 14, 15, 16, 17, 18. 22 is the vibration, but we're not going to cover it. So that's why I've just written it here as self-study. And it's put on week number 16. Our EBIT learning outcome is only one, that we are able to solve engineering problems. Course learning outcomes are mentioned here corresponding to each chapters. It's useless to discuss this right now, because when we are going to discuss the problems itself, you will understand them. Attendance policy is very simple. You should be attending all the lectures, and it is good for you because it's going to give you a good preparation for the exam, and other things are same. So that was all about the syllabus. Inshallah, I'm going to upload the syllabus file and all the lecture material on the Blackboard. So anybody has any question, you can ask. Okay. Anything anybody want to discuss regarding the grading policy, regarding the timing of the quizzes, midterm exam? You are able to hear me, right? Okay. Good. Okay, it's fine if nobody has to ask anything. I can continue with our first lecture, which is regarding chapter number 12. When will be the office hours? This is a very good question. Suppose if I have an office hours, how we are going to discuss? I mean, so I put it as open. Like for example, if a group of students have some issues, so what you can do is that you can ask your class leader. She can arrange a time with me, and then I can be available on Zoom for that, and it will be kind of a help session for the students. So let it be open. Whenever needed, we can conduct that. Is it okay? Okay. Okay, so let's start with our lecture today. There are a lot of theoretical explanations and things here in the lectures. Okay, a lot of material is for you to read yourself. Whatever the important things, I'm going to be discussing them with you during the lecture. So applications, what are the applications of dynamics? You go through, read yourself. This thing I've already mentioned to you. This is basically branch of mechanics, engineering mechanics, statics and dynamics. Statics you already covered. Dynamics we are covering right now. Then within the dynamics, you have kinematics, kinematics is about the study of the motion itself. Kinetics is basically it's a complete picture where we keep into consideration the forces acting on the body itself as well, along with the motion of the body. Okay, let's discuss a little about vectors and scalars. This is kind of a repetition. You already studied this thing in statics. So vectors and scalars, what's the difference about that? Scalars are something which are just numbers. Vectors means they are not just numbers, but there is a direction associated with it. So if it is just magnitude, that's a scalar. If it is magnitude with direction, that's a vector quantity. So for example, speed is a scalar quantity, mass is a scalar quantity, no direction. Temperature is a scalar quantity, no direction. However, when we talk about velocity, then velocity has a specific direction. When we talk about force, it has a specific direction. Force will be applied in certain direction. Weight has a certain direction. Similarly, momentum, acceleration. So these are the examples of vectors. One important point here of discussion is what is the distance, what is the difference between distance and displacement. Okay, before continuing further, let me just explain thing to you here. Uh, Normally when I'm giving lecture face to face, I can see the students. I can actually judge from their expression whether they are able to understand me or not, whether they're getting the subject or not. But when I'm giving the lecture here online on Zoom, I I'm just talking to my own self, and I don't know whether you are actually getting my point or not, or you're understanding the subject or not. So my request to you is that in case at any point if you feel that now you are not getting me, okay, now you're not understanding the subject, please feel free to interrupt me. Let me know that okay, now you are not uh, understanding the subject, okay, so that I can focus myself over the part where you are not being able to understand it very well. Otherwise, I might continue without knowing that you are not able to understand the material. Because since I cannot see you, so I cannot judge your expressions, and I'm not able to find out whether you are able to understand the material or not. So I will continue, and time to time I will stop and ask that, okay, if anybody has any question, you can ask. If nobody has any question, I will assume that you understand everything, and I will continue forward. Anyways, most of the concepts here are very easy and kind of a repetition of what you have already done before in statics. So inshallah, it's not going to be a big problem. But anyways, this dynamic course is a course where things are built upon each other. So if you don't understand one thing now, tomorrow you're going to have a problem in some other thing. So I hope that you keep up with me, and let me know if you are understanding the subject or not. So let's continue onward from here. Uh, there is one important point between distance and displacement. When we talk about distance, distance means the total path traveled. Okay, so total path travel. Uh, it's but whenever we talk about displacement, it doesn't mean the total path traveled. It means what is the net distance traveled? What is the direct distance traveled from point A to point B? So displacement is the shortest distance. Okay, uh, distance, when we just say distance, it means the total distance. Okay, so when we talk about the displacement, it is the shortest distance. So now one question arises: is it possible for displacement to be bigger than distance? No, it's not possible, because displacement is the shortest distance. At max it could be equal to distance. Displacement could, at max, displacement could be equal to distance, but it cannot be bigger than distance. So distance is normally bigger than displacement because it's the total path traveled. So for example, a body traveled from here to here, then here to here, then here to here, then here to here. So that's the total distance the body traveled. But when we talk about the displacement, so displacement will be from start point to the end point net distance. It is just this much. So displacement is like this. Okay, suppose if the body only traveled from here to here, okay, then in this case the distance and displacement are same. So displacement is normally smaller than distance, but displacement can never be greater than distance. At max, what's possible is that displacement and distance are same. So okay, let's have a small numerical associated with it. A particle started at point A and reached point F. So it started at point A like this. Initially, it moved from point A to B, 8 kilometer in 5 minutes. Then B to C, 2 kilometer, 2 minutes. Then C to D, 4 kilometer, 3 minutes. Then D to E, 2 kilometer, 2 minutes. Then E to F, 9 kilometer, 5 minutes. Now we need to know that what is the total displacement. Okay, so when we want to find out what is the total displacement, so it will be the shortest distance, means from start point to the end point. So that's inclined line will be the displacement. So how can you find the length of this line? It's a simple problem of geometry. We can draw a right angle triangle here. That's a right angle triangle here. Okay, so we can find this distance. How can we find this distance? Okay, so we can find how much it traveled to the east, then how much total it traveled to the west. Difference between that will be, so if I consider how much it traveled to the east, so it is 8 kilometer plus 4 kilometer, 8 plus 4, 12. And how much it traveled to the west? 9 kilometers. So 12 minus 9, 3. So this will be 3. Okay, and then how much it traveled uh, in the upward direction? Okay, so it's 2 kilometer here and 2 kilometer here, so 4 will be here. Okay, so we have 3 here, 4 here. Now it's a right angle triangle. You can apply the Pythagoras theorem, okay, and you can find out what is the length of the hypotenuse. It's simple. So that will be 5 kilometer. So the displacement will be 5 kilometer. Now we need to find the average speed and average velocity. Remember, when we talk about the speed, it's a scalar quantity and it is linked with the distance. Whenever we talk about velocity, so that's the vector quantity and it is linked not with the distance, it is linked with the displacement. Okay, so speed will be the distance over time. So time, how much it took? 5 minutes plus 2 minutes plus 3 minutes plus 2 minutes plus 5 minutes. That's the total time it took. But what is the distance? Distance is 8 kilometer plus 2 plus 4 plus 2 plus 9. So that's the total distance. But when we talk about the displacement, it is just this hypotenuse which you found, 5 kilometer. So average velocity will be 5 kilometer over 17 minutes, but average speed will be 25 kilometer over 17 minutes. So you find the average speed, you find the average velocity. It's actually a simple problem. So anybody has any question in it? Anybody wants to ask anything? Please feel free to ask. Good. Is it clear? Okay, let's move ahead. Types of motion. There are two types of motions, rectilinear motion, curvilinear motion. By the name, it's very clear. Rectilinear motion, motion in a straight line. Curvilinear motion, motion in a curve. So motion over circular path, that's a curvilinear motion. Okay, so nothing more to explain in it. Let's move forward. Okay, now let's discuss about displacement. How do we represent displacement? Okay, normally when I give a face-to-face lecture or the lecture in the class, there is a board and I have the leverage of writing things on the board. Now I don't have any board here, or writing on a board here is much more difficult compared to do it in the class. So what I did is that I wrote things on the paper which I normally used to write on the board and take a picture of it so that we can discuss about them. Today, you are going to study 10 equations, 10 fundamental equations, very important, okay? And step by step, I'm going to go through with those equations with you, and I want you to understand them very well, okay? At any point, if you feel any difficulty, do let me know. Normally, when I'm opening the screen, there is the participants window here, and there is a chat box here, which is covering my screen. I don't know. Do you see these windows as well? The participants and the chat window?
No, we can't. We can't see it.
So that means my screen is totally visible to you
Yes.
without any hindrance. Okay. So let's have a look at it. Displacement. S is displacement. Normally in this book, we represent S as displacement. Okay. However, in later, when you move towards chapter number 14, 15, you will find that they use S for another for another variable as well. So it becomes a bit complicated and you get a little confused. Students get a little confused. For now, S is displacement. It's a vector quantity. Very clear about it. Okay. So first equation, if you know displacement and you know time, okay, you can find out that how is the displacement varying with time. So change in displacement with time. Let me use the box maybe. Yeah. Okay. So change in displacement with time, that is the velocity. Okay. Displacement is normally given in meter, right? So time in second. So what will be the unit of velocity? Meter per second. Okay. So velocity is, we write it in the differential format. When we say ds by dt, it means the change in displacement with change in time. That's velocity. It's meter per second. Okay. And also mathematically, we can also write it as s dot. Something dot means d by dt. Now, I don't know whether you know the symbolism or not in differential equations, but in this book, it is used, the symbolism. So anything with a dot means this thing d by dt. So here, when we say s dot, it means ds by dt, which means it is velocity. This is the first equation, very important equation. Do you understand it or not?
We understand.
Okay, good. Just a minute. Okay, so let's move ahead.
There is a student who didn't understand.
Excuse me, anybody want to say something?
The last point is not clear for some.
Participants. Okay.
Can you repeat, doctor, please?
Okay. I said that S is displacement, okay, and V is velocity. And what is velocity? Velocity is the change in displacement per unit time. Okay, that's the speed. How the displacement is changing, how the position is changing with time. That's the speed, which is velocity. Okay, in vector format. Since we're talking about not distance, we're talking about displacement. So change of displacement with time is velocity. So it is represented as V or ds by dt, or we can write it as s dot. S dot means it's the same thing. So s dot is the same thing, which means ds by dt. So something over dot means d by dt. Is it clear or not?
Yes, clear.
Yeah, okay. So this is our first equation. Now let's move over to the next equation. The next equation is that we can have the variation of velocity with time as well, and that is known as acceleration. And physically it means what is the rate of change of speed. Okay, so there is a change in speed, that is velocity. Okay, but what is the rate of change of that speed? How quickly it is changing, or how slowly it is changing. So that is acceleration. So acceleration is basically what it is, dv by dt, change in velocity with respect to change in time. Or we can write it as v dot. V dot is dv by dt, but we know that v is ds by dt, so I can just write the formula of v here. So it will be d by dt into ds by dt becomes d square s by dt square, so which is equals to s double dot. So s double dot or d square s by dt square or v dot or dv by dt or a, these all are the same things, and they all are used in the book. So you should know this symbolism. So this is my equation number 2. Is this thing clear or not? Good. Anybody has any question, you can ask. Okay. Okay, so let's move ahead. So now you got two equations. One equation is for velocity, other equation is for acceleration. Okay, now from this first equation, we have v equals to ds by dt. That means I can write it as dt equals to ds by v. And similarly, from the second equation, we have a equals to dv by dt. So I can write it as dt equals to dv by a. Now I can equate the two dt's. So it becomes ds by dv equals to dv by a. ds by v equals to dv by a. Or I can write it as a ds is equals to v dv. So that becomes the third equation. Do you understand this third equation? Is it clear or not? I use equation 1 and 2 to develop equation number 3.
Not clear.
Lejine, you said something, I couldn't hear you.
Yes, it's not clear.
Not clear?
Yes.
Okay, so let me. So we have this equation, v equals to, v equals to ds by dt. Okay, we can use this equation to write it like this. Is it clear? dt equals to ds by v.
Yes.
I just switch the positions of v and dt. And we have another equation, a equals to dv by dt. Okay, can I write it here like this? dt equals to
Yes.
dv by a. Just switch the
Yes.
positions of a and dt. Is it,
Yes. Yes.
is
It's
it clear?
Yes.
Now I have two equations here. dt equals to ds by v and dt equals to dv by a. Okay, can I equate the two? Because both are dt.
Yes.
Okay, so this becomes this. Now once I have this thing, I can write a ds is equals to v dv. Is this thing clear or not?
Yes. Thank
It's
you.
clear? So that becomes
Yes.
our third equation. So we have developed three equations here. Equation for velocity, equation for acceleration, and then now if you see here, in the equation for velocity you have time. In the equation for acceleration you have time. But when we equate the two, so now this equation has no time factor. ADS is equals to VDV, there is no time. Okay. So anyways, we have three equations here. Anybody has anything which you do not understand in these equations, let me know. Okay, let's move ahead. Look, do you understand the difference between differentiation and integration? Differentiation and integration are opposite to each other. In differentiation, you are actually finding the rate of one thing with respect to the other. In integration, you are actually accumulating something. So it's summing up everything. So differentiation and integration are opposite to each other. Okay, so if we know the velocity, now focus here. If we know the velocity, if we know the distance, we can find velocity. Okay, by differentiation. Suppose if we know the velocity, can we find the distance?
Yes, why?
We can do it, but in that case, what we have to do is, instead of differentiation, we need to integrate. Okay, so v equals to ds by dt. So that means ds is equals to v into dt. So ds is equals to v into dt. Now we can integrate this equation from s naught to s and t naught to t. So this will give us the distance. So if we have the velocity, we can integrate to find the distance. If we have the distance, we can differentiate to find the velocity. Do you understand this relationship or not? This is important here. If you have, once again, listen carefully. If you have distance, you can differentiate to find velocity. If you have velocity, you can integrate over time to find the distance. Okay? Do you understand this concept or not? Is it clear or not? Differentiation and integration are opposite to each other. Okay. If you understand this concept, then this becomes your equation number 4. See, this is equation number 4. So equation number 4 is coming from equation number 1. From equation number 1. Equation number 1 was the differential format. Equation number 4 is the integral format of it. In equation number 1, you know the distance and you wanted to find out the velocity. In equation number 4, you know the velocity and you need to find the displacement. Is it clear? Okay. Let's move ahead. Like from equation number 1, similarly from equation number 2, we can use it the same way. Now look here. In equation number 2, if you know the velocity, you can find acceleration by differentiating it over time. In the same way, if you know the acceleration, you can integrate it over time to find out the velocity. If you know the velocity, differentiate to find acceleration. If you know acceleration, integrate to find velocity, opposite of that. And this becomes your equation number 5. Is it clear or not?
So doctor, time will is known in every equation, right?
You're
Every
speaking so
problem.
slowly, I cannot hear you properly. Can you speak a little loud?
Okay. Time will be known in all problems.
Yes, time will be known in this problem. Sure.
Okay, thank you.
Because you have to integrate over time. So if time is not known, then how can you find the velocity? Right? So you're right. Time is known here. So time is known and acceleration is known. Time and known and velocity is known. So time and velocity are known, you can find displacement. Time and acceleration known, you can find velocity. Is okay? So we have a third equation. In the third equation, time is not needed. Suppose if the time is not known, okay, then if you have the, if you integrate this equation, then suppose if you have the velocity, you can find out the displacement, or if you have the displacement, you can find out the velocity. But in any ways, this third equation is from the integration, this equation number 6 is from the integration of equation number 3. And this equation is also a very valuable equation, and you will see that it will give some valuable results in future. But like the way we can integrate equation 1 and 2, we can also integrate equation number 3, and this becomes our another fundamental equation. So right now, what I have developed in front of you are 6 fundamental equations. 3 are the differential format, between velocity, speed, acceleration, velocity, or acceleration speed in this format. Okay, and then ADS is equals to VdV. These 3 are the differential format equation, equation 1, 2, and 3. Equation 4, 5, and 6 are the integral format equation. Equation 1, 2, and 3 are the differential format equation. Equation 4, 5, and 6 are the integral format equation. Okay, so 4 is if you know the velocity, you can find displacement. 5 is if you know the acceleration, you can find velocity. And 6 is the integral format of equation number 3, which is ADS is equals to VdV. That the integral format is if you just integrate this equation. Anybody has any question in the understanding of these 6 equations, please let me know. Are these 6 equations clear or not? As I told you, today in our class, we are going to develop 10 equations. We are going to study 10 equations. Okay, these are the first 6 equations that you studied. Anybody has anything to ask? Okay, let's move forward. So we have developed equation number 1, 2, 3, 4, 5, 6. Now 4, 5, 6 were the integral format equations. Okay. Now suppose if the acceleration is constant. Suppose if the acceleration is constant. So what will happen? Now let's see equation number 5. If the acceleration is constant, then this A is a constant in this equation. What will happen to a constant if it is inside integral? It can come out of the integral. A constant comes out of the integral. So A will become AC, which is now a constant. A will become AC, which is now a constant, and it will come out of the integral. Okay. So now let's integrate it. So if we integrate it, it becomes integral dV will become V, integral dt will become T. So we apply the limits. Let's say that T initial is 0. So from 0 to T and V0 to V. So it becomes V minus V0 equals to AC T minus 0. Or it becomes V equals to V0 plus ACT, where V0 is the initial velocity, V is the final velocity. T0 was the initial time, which we say is 0, and T is the final time. So V is equals to V0 plus ACT, means final velocity is equals to initial velocity plus constant acceleration multiplied by time. This is another fundamental equation. And how do we derive this equation? We derive this equation from the integral format, equation number 5, considering acceleration constant. Do you understand this equation or not? This becomes equation number 7. Is there anything in this equation that you do not understand? Please ask. Why I am driving these equations and why I'm discussing these things with you, because in the lecture problems you will find that you will keep on using these 10 equations a lot. At least you should know that how do we drive these equations, where these equations come from. They are coming from each other. So from equation 1 to become equation 3, then from equation 1 2 3 becomes equation 4 5 6, then using equation 5 for constant acceleration it becomes equation 7. You see this thing? The equations are coming from one another. They're driving from each other. So at least you should know that which equation is coming from where. Anybody has any questions so far? Is it clear? Okay, I can repeat equation number 7 once again. You see equation number 5, it's a differential format. dv equals to a dt integral. Okay, so integrating, we apply the integrating limits, initial velocity to final velocity, v0 to v. Integrating limits, initial time to final time, t0 to t. Okay, now suppose we have constant acceleration. Constant acceleration means something is constant. No, it's not a variable. Okay, so what happened to a constant when it is inside integral? It comes out of the integral. Whenever you have a constant inside integral, it comes out of the integral. So A will become AC. Suppose if it is a constant acceleration, then it will come out of the integral. So now what do we have? Integral dv, v0 to v equals to AC integral dt, t0 to t, where t0, let's say it is 0. Initial time is 0. Now when you integrate it, so integral dv will become v, integral dt will become t. Applying the limits 0 to t, v0 to v, it becomes v minus v0 equals to AC t minus 0, or v equals to v0 plus ACT. So this is the equation for constant acceleration. Equation 7 is the equation for constant acceleration. Where it is coming from? From equation 5, by putting acceleration as constant. Is it clear? Okay. So if equation number 7 is clear to you guys, now remember one thing. Equation 7 you can only use if you know the acceleration is constant. Suppose you have a problem in which acceleration is not constant. Can you use equation 7? No, you cannot use equation 7. Why? Because you drive equation 7 by assuming that the acceleration is constant. If the acceleration is not constant, you cannot use this equation. Okay, so as we are driving the equations, we should also know that under what condition we drive the equations, so that we can know where to use it. Because we drive the equation here, equation 7, by assuming constant acceleration. So now we know that this equation can only be used if the acceleration is constant. Suppose you have a problem in which the acceleration is not constant and you use this equation, then this is a mistake. And when you do mistakes, marks are detected. So it's better that we know when to use which equation, so that we don't do mistakes and our marks are not get detected. Okay, so let's move ahead. If anybody has anything to ask related to this equation 7, please ask. Otherwise I will move ahead. Okay, so we had this equation number 5. We use it for constant acceleration to find out an expression for velocity. Now look here, this is an expression for velocity. V is equals to V naught plus ACT. And this is an expression for velocity if the acceleration is constant. Now what we want to do is that we want to use equation number 4 for constant acceleration. But do you see any acceleration inside equation number 4? There is no A. But there is a V. Now we know an expression for V for constant acceleration. So why don't we use equation 7 in equation number 4? Okay, so what we are going to do is that we want to find an equation for constant acceleration using equation number 4. But in equation number 4, there is no A. So how do we apply constant acceleration? There is a V here. And we have an expression of V for constant acceleration already, equation 7. So let's use it here. Okay. So when we use it here, how would it look like? You see here, ds integral s naught to s is equals to integral. Instead of V, I'm going to put V naught plus ACT, because this V is for constant acceleration. Okay, so I substitute here, and now I need to integrate. So integral ds will become s with applying the limits s naught to s, it becomes s minus s naught. And what will happen inside? So v naught is a constant. It was the initial velocity, that's a constant. So it becomes v naught t when you are integrating against dt. Okay, so it becomes v naught t plus ac. There is also a t here, so this t becomes t square upon 2. And we apply the limits from 0 to t. So it becomes s is equals to s naught plus v naught t plus half act square. So this becomes our equation number 8. Do you understand this equation or not? Very important. These 10 equations which I am driving today in front of you are going to be the fundamental for the whole course. It's going to continue from chapter number 12 and will continue till chapter number 18. So understanding these are very important. You understand them, you understand half of the dynamics. Do you understand equation number 8 or not? How do we drive it? We drive using equation number 4 for constant acceleration, but there was no acceleration inside. So what we do is that we use the expression for velocity, which we now know for constant acceleration as equation 7. We substitute it into this equation, okay? And here we got, after integrating, we got an expression here. Again, remember, equation 7 and equation 8 are both for constant acceleration. If you use equation 7 and 8 for a problem where the acceleration was not constant, this is a mistake. And you are not going to do this mistake, okay? Equation 7 and equation 8 are for constant acceleration. How do we drive equation 8? We had equation 4, we substitute equation 7 into equation 4, we got equation 8. Is it clear? Anybody has anything not clear, please ask. Okay, I presume that everybody understand it. Okay, so let's move ahead. So we used equation 5, we used equation 4. So to be fair, we should also use equation 6. Okay, so let's use equation 6. Now in equation 6, what do we have? We have acceleration. So for constant acceleration, A will be replaced by AC, and it will go out of the integral. But we also have a V here. And we need to have an expression for V as well, but we already have that expression for constant acceleration. Equation 7. So what we are going to do is that now we are going to use equation 7 inside equation 6. So 7 will be used inside equation 6, while at the same time A will come out of the integral because it is constant acceleration. Okay, So let's do that. So look here. This is our equation 6. A will come out of the integral. Okay. A will come out of the integral. It will become AC. Integral ds s naught to s is equals to, and here we have v dv. Since we have dv here, okay, I'm sorry, I made a mistake. We do not have to replace v equation 7. Why do we do not need to replace equation 7? Because we have v here and it is a differential of dv. So we don't need an expression as a function of time. Previously, why do we needed to do that? Focus here. Previously, we needed to replace v as a function because here it was dt. Since here it was dt, okay, so we needed v as a function of time. Okay, so this becomes v as a function of time, which could be replaced here. Now, in this equation, we have dv. We have dv here. It's not a function of time. We already have v here. So we don't need to replace equation 7 here. So my mistake. Okay. So here, only thing what will happen is that AC will come out of the integral and this v dv will become v square upon 2. We apply the limits, v naught to v, s naught to s. Okay. So it becomes AC constant acceleration s minus s naught equals to v square upon 2 minus v naught square upon 2. 2 will go to the other side. It becomes 2ac s minus s naught equals to v square minus v naught square, and so it becomes v square equals to v naught square plus 2ac s minus s naught. This becomes equation number 9. Do you understand the application of equation number 9 or not? How do we determine equation number 9? Is this thing clear to you or not? Is there anything in it which is not clear? Please feel free to ask.
Doctor, can you repeat, please?
Okay, let me repeat again. Okay, so you see here, this was equation number 6. This was equation number 6. Okay, so what we need to do is that now we need to find an equation for constant acceleration using equation number 6. Okay, so what we do is that A becomes constant acceleration, so it becomes a constant, comes out of the integral, and V is just integrated. It becomes v square upon 2. We don't need to replace it as v equals to v naught plus act. Why? Because here we have a differential of dv. Okay, so v is there and we are differentiating with respect to v, so we don't need an expression for v separately. This is the problem of the mathematics. When to find an expression of something with respect to the other. We have to see based on which we are differentiating. If we were differentiating here with respect to time, then we need an expression of v with respect to time. But we are not differentiating with respect to time. We are here, the differential is with respect to v itself. So we don't need an expression for v. We can directly integrate v and it will become v square upon 2. Okay, so now we just apply the limits v naught to v and apply the limits here s naught to s and just substitute the values, and in the end we got this equation v square equals to v naught square plus 2ac s minus s naught. I don't know whether I'm able to explain thing or not to you. Please let me know. Is it clear or not?
Yes, it's clear. Thank you.
It's clear? Okay.
Yeah.
So this becomes our equation number 9. Very important. Okay. Now, if you see here, all the equations are deriving from each other. In the end, I'm going to summarize things to you again. So this becomes equation 9. Remember, equation 9 and equation 7 and 8, they are for constant acceleration. You use equation 7, 8, and 9 for a problem where the acceleration is not constant. That's a mistake. Okay. So it is always better to know that which equation to use where. Okay, so now we have this. Now let's have a special case. From equation 7, 8, and 9, suppose we have a constant acceleration which is 0. Suppose we know now the value of constant acceleration, and the value of constant acceleration is 0. So how would the equation becomes? So let's see equation 7. What will happen to equation 7 if AC is 0? It's just V equals to V naught. If AC is 0, V equals to V naught. So by using equation 7, V equals to V naught. But that's not a useful equation. It's kind of a useless equation. Let's see about equation number 8. What will happen to equation number 8? If AC is 0, this term will go to 0. If AC is 0, this will become 0. Okay. And so the equation becomes what? S is equals to S naught plus V naught T. Right? So it becomes S is equals to S naught plus V naught T. Suppose S naught is 0. S naught is the initial distance from where a body started to move. So if we consider that as a reference point, so S naught will be 0. So it becomes S is equals to VT. That becomes equation number 10. S is equals to VT is equation number 10. It is a special case where constant acceleration is 0 when applied to equation number 8. Is this thing clear or not? Anybody has anything which is anything to say which is not clear? Okay, now let's discuss about equation number 9. What will happen to equation number 9 if we say that constant acceleration is 0? So AC 0 means this term will become 0. Okay, so this term will become 0. So it becomes what? V square equals to V naught square. It's again a useless equation. So this equation is actually not a useful equation. It's a useless equation. This is also a useless equation, but this equation is useful. So we have 10 equations here. Let me summarize the 10 equations that I just developed with you guys. Okay, let me summarize all of them once again. So first we have the equation. If we know the displacement, we can find what is the velocity. Differential form of equation, V equals to ds by dt. Similarly, if we know the velocity, we can find acceleration. That's the second equation, A equals to dv by dt. Using equation 1 and 2, we get AdS is equals to VdV. That is equation number 3. So in the equation number 3, there is no time factor. So 1, 2, 3 becomes the 3 fundamental differential equations. Okay. Using equation 1, 2, and 3, we can write all the 3 equations in the integral format as well. That becomes equation 4, 5, and 6. So now 1, 2, 3 are the differential form of equations. 4, 5, and 6 are the integral form of equations for equation 1, 2, and 3. 4 for 1, 5 for 2, 6 for 3. Then after that, now we have equation 4, 5, and 6. Suppose we have constant acceleration. For constant acceleration, equation 5 will give an expression for velocity as a function of time. So equation 5, when applied for constant acceleration, will give a equation for velocity as a function of time. We can use this velocity as a function of time in equation 4 because here we have dt. And we can find another equation, and this is also equation for constant acceleration, which is s equals to s naught plus v naught t plus half act square. That's equation number 8. And we can also integrate equation number 6. Okay, here we don't need velocity as a function of time because the differential is dv, it's not dt. Okay, so we can also use equation number 6, and once we use equation number 6, we will get equation number 9 if we integrate. Okay, so that becomes our another fundamental equation. Now we have equation number 7, 8, 9 for constant acceleration. Let's talk about a special case when that constant acceleration is 0. So equation 7 and 9 are quite useless. It just gives v equals to v naught. But equation 8 gives s is equals to v naught t, which becomes equation number 10. So these are the 10 fundamental equations, equation 1 to 10, all very, very important. You are going to use these equations from chapter number 12 onward till chapter number 18, all of them, and they are very important, and you should know how you drive them and how you get them, okay? So these are the things which I used to write on the board while explaining it to the students, but here, while I'm giving the online lecture on Zoom, it is not possible that I can write things on board. So I already wrote them on a piece of paper and trying to explain it to you in this way. So I don't know if things are clear to you or not. You're welcome to ask any question if you want. Please ask. Let me know if these things, whatever I have explained to you so far, are clear or not.
Doctor,
Yes.
can you please upload this sheet on Blackboard?
Sure. I will upload everything, you know, because I am the advisor for the mechanical energy engineering department. Last 3-4 days for me were like hell, and still the hell is not yet over. The registration is going on, and I really have no time at all. However, as soon as this registration things are over, then I'm going to streamline my lectures thing. Okay, so I'm going to upload these slides, whatever the pages I write myself, everything on the Blackboard. So you will have all the material, but just wait a little until things get a little streamlined with me.
Okay, thank you.
Okay. But for me here, important point is that, do you understand all the things which I'm trying to explain it to you or not? If you understand them, my job is going fine. If you don't understand, let me know. Okay, it seems things are clear. Okay, so let's move back to the slides. Okay. So we're discussing about kinematics. Okay, velocity, d v equals to ds by dt. Okay, this is velocity. There is some description written. You can just read it yourself. I don't need to go into that. Okay, a particle moves from point P to P dash as shown in the figure. So that was point P. The particle first moves in this direction and then make a U-turn and then return back to point P dash. Okay, what is the average velocity? What is the average speed? Average velocity, I told you, velocity depends upon displacement. So it doesn't matter what was the path the object took. The only thing matters is what is from initial point to the final point, what is the distance. So from initial to final point distance is minus del S. So it becomes minus del S by del T. What is the average speed? When we talk about the speed, now it's not just the displacement. We need to consider the whole distance. The whole distance was st. So the whole distance was st. So st divided by del T, that becomes the average speed. So it's a simple thing. And I'm going to move forward, assuming that you understand it. If anybody has any question, you can ask. You're going to stop me in between, okay? Okay, a particle moves along a straight line such that its position is defined by s is equals to t cubed minus 3t squared plus 2 meter. Determine the velocity of the particle when t is equals to 4 seconds. Now look here, what is given? S as a function of t. What do you need? Velocity. Okay, come back here. We have s as a function of t, we need velocity. Which equation do we need to use? Equation 1. Okay, so we have v equals to ds by dt. We have s as a function of t, so we just differentiate it. So t cubed becomes 3t squared minus 6t, and now we just substitute t equals to 4 seconds. We can find what is the velocity. I think it's a pretty simple thing. There's nothing complicated about it. So let's move ahead. Acceleration. Acceleration is a equals to dv by dt or d square s by dt square. Okay, and using those equations we can find ads is equals to vdv. That was our equation number 3 that we developed. A particle moves along a straight line such that its position is defined by s is equals to t cubed minus 3t squared plus 2. Determine the acceleration of the particle when t equals to 4 seconds. Now we have s, we need to find a. Okay, so we need to move it in 2 steps. Okay, so first what we do is, because we have s as a function of t, we can find velocity. Then once we have velocity, we have v as a function of t, we can find acceleration. We move in 2 steps. Okay, so first step, find v equals to ds by dt. That becomes 3t squared minus 6t. Then a equals to dv by dt. So it becomes 6t minus 6. Just substitute the value of t equals to 4 seconds. You can find the acceleration at that time. Anybody has anything to ask? Any question? Wherever I think that this is a bit more complicated thing and I need to spend more time on it, I'm going to spend more time on it. Otherwise, you will find me moving with the rocket speed. Okay. So still, I give you the permission that if any one of you feel that you do not understand anything, you can interrupt me, stop me at that point, so that I know that you are feeling trouble and I can clear things for you. So anybody has anything to ask? Okay, if nobody has anything to ask, let's move forward. A particle moves along a straight line such that its position is defined by, now it's a more complicated equation, t cubed minus 12t squared plus 36t minus 20. Describe the motion during the time interval. So here different times are given, 0, 2, 4, 6, 9. So you can find the value of s, you can find the value of v, you can find the value of a, v equals to ds by dt, a equals to dv by dt. So you have all these equations, just substitute with values of time in these equations and complete the table. There is nothing more into it. Okay, so next, we have the 3 fundamental equations here. That was equation 1, 2, and 3 in the picture that I have shown you. Okay, using these equations, we can determine equation 4, 5, and 6. Now, those were the differential format. These are the integral format equations. Okay, so this equation 4, 5, and 6. So let's move ahead. Okay, let's see this problem. The car on the left in the photo and in figure 12.2 moves in a straight line such that for a short time its velocity is defined by v equals to 3t squared plus 2t, where t is in seconds. Determine its position and acceleration when t equals to 3 seconds. And the initial condition is given when t equals to 0, s is equals to 0. Now see one thing here. What is given? Given is this, velocity as a function of time. Now what do you need? You need to find position, okay, determine its position. So you need to find s and acceleration, a. So let's look here, okay, we have velocity as a function of time. So if we want to find a, then we have to differentiate with respect to time to get a. But if we want to find s, we need to integrate with respect to time to get s. So we had v as a function of time. We had, let me write here, we have v as a function of time. So when we need to find a, we have to differentiate it. When we need to find s, we need to integrate it because we have v as a function of time. Okay, so this is what is needed to be done in this question. One time integration, other time differentiation. Okay. Okay, so let's no problem. So we have v as a function of time. So v is basically ds by dt. So if you want to find s, you have to integrate. So integrate, initial time was given when time is 0, displacement is 0. So just integrate it and substitute the values, you will get an equation. So you need to find when t equals to 3 seconds, as was given in the question. And when we need to find acceleration, we differentiate. So d by dt, we substitute the value of the variable for v, which is 3t squared plus 2t, and differentiate it with respect to time, you get the acceleration. Substitute t equals to 3 seconds, you get the acceleration. Is there anything which is not clear in this question? Please ask. Is there anything which is not clear in this question? Please ask. You feel you don't understand anything, you can ask me to repeat, no problem. Actually, this is very simple problem. There wasn't really anything much difficult to it. So that's why. Okay, let's move ahead. A particle moves along a horizontal path. A particle moves along a horizontal path with a velocity of v equals to 3t square minus 6t, where t is the time in seconds. If it is initially located at point O, determine the distance traveled in 3.5 seconds and the particle average velocity and average speed during the time interval. They made the problem to move to go through the differentiation and integration, but it was not really necessarily needed. It's already mentioned that the particle initially was at point O, then it initially moved from to 4 meters in the west direction in 2 seconds, and then after that at 3.5 second it was at this position where it has traveled in the east direction 6.125 meter. Okay, so total time it took to come to this point was 3.5 seconds. Now, when we need to find the average velocity, we have to consider the displacement. So displacement from the start point to the end point is only 6.125 meter. But when we have to find the average speed, then we have to use the whole distance covered. So the whole distance covered will be what? 4 meter in this direction, then reverse 4 meter again to return back to O position, and then 6.125 meter. So 4 plus 4 plus 6.125, that is the total distance traveled. Okay. So it's basically this average average velocity. It will be 6.125 divided by 3.5 second. But when we talk about the average speed, it is 14.125 because it will be 4 plus 4 plus 6.125. Okay, and so that will be the average speed. So this was the main thing in this problem, to find out the average speed and the average velocity. Anybody has anything to ask? Okay, constant acceleration. I went through with you guys here that when we have constant acceleration, then equation 4, 5, 6 becomes equation 7, 8, and 9. Okay, so this is the same thing here. Equation 4, 5, 6 becomes equation 7, 8, 9. Okay, but I went through in detail with you. So this is how this integration is done. So let's have this problem, example 7 here. Okay, car A starts from rest at t equals to 0. So we have, this is our car A. Let me write here, this is our car A. This is our car A, it starts from rest at t equals to 0 and travel along a straight road with a constant acceleration of 6 feet per second square. So initially there was a constant acceleration. Remember, car A is initially having a constant acceleration, AC, until it reaches a speed of 80 feet per second. Afterward, it maintains its speed. What do you mean by maintain its speed? Maintaining the speed means the velocity is same. Velocity is same means there is no acceleration. So that means now there is still an acceleration, but that's the constant acceleration with value equals to 0. Okay, so after it reaches 6 feet per after it reaches a speed of 80 feet per second, then the acceleration of car A, AC, is 0. This was about car A. Wallahi, it's very hard to write things on the laptop when you don't have a board in front of you. Anyways, afterward it maintains space. Okay, also when t equals to 0, car B located 6,000 feet downward Okay, so it is 6,000 feet away from car A initially down the road. It's traveling towards A at a constant speed 60 feet per second. Okay, so this was initially traveling with a constant speed 60 feet per second. So there is no acceleration here. For this, initially AC is 0. Okay. Determine the distance traveled by car A when they pass each other. Remember, they both are moving towards each other. They both are moving towards each other. This is moving in this direction. This car is moving in this direction. Eventually, they will pass each other. So we need to find that what is the distance traveled by car A. What is the distance traveled by car A when they both pass each other? So first of all, before moving towards solution of the problem, do you understand the problem statement or not? So once again, car A starts from rest and it travels along a straight road with a constant acceleration. Remember, when it is moving with a constant acceleration, which equations you can use? You can use oh, this, yes, so which equation you can use when it is moving with the constant acceleration? You can use equation 7, you can use equation 8, or you can use equation 9. Okay, and when the car is moving with a constant speed, afterward it maintains its speed. When the car is moving at constant its speed, which equation you can use? Then you can only use equation number 10. That's the point when constant acceleration is 0. Okay, so car A starts from rest and travels along a straight line with a constant acceleration 6 feet per second square until it reaches a speed of 80 feet per second. Afterward, it maintains this speed. Also, when t equals to 0, car B located 6,000 feet down the road is traveling towards A at a constant speed of 60 feet per second. Determine the distance traveled by car A when they pass each other. Okay, I need to stop here before moving towards the solution. First of all, I want to know, do you understand the problem statement or not? Anybody don't understand the problem statement? Okay. So, because before moving towards the solution, the first important thing is that we should know that, yes, you do understand the problem statement. Then we move towards the solution. So what do we need to find? We need to find the distance. Distance traveled by car A. The two cars are moving towards each other and they will pass each other. The time, the instant when they pass each other, when they pass each other, at that instant, how much distance has been traveled by car A? Okay, so let's move towards the solution of the problem. Okay, now for car A, there are two specific regions of travel. Okay, there's a first initial period when the car A was accelerating at at a certain acceleration speed. Okay, so that was the acceleration speed was 6 feet per second square. Okay, that was the initial period, and after that acceleration becomes 0. So there are two regions. So in one region there is acceleration, which is 6 feet per second square. In the other region, acceleration is 0. And for car B, there is only one region where the acceleration is not, where there is no acceleration. So let's talk about car A. So in the initial period, it is said that the car A starts from rest. So what is the initial velocity of car A? V equals to 0. So now let's see what equations we can use. Okay, so we have equation 7, we have equation 8. Let's first use equation number 7. So v is the final velocity and v naught is the initial velocity. Initial velocity is 0 because it's mentioned that car A starts with a at rest. So this is 0. Okay, and final velocity is given. How much is the final velocity? It is 80 feet per second. So this is known. Okay, acceleration is also given. Okay, whatever the acceleration of the car was is given, it's 6 feet per second square. So we can find that what was the time taken by the car while it moved from 0 velocity to 80 feet per second. We are talking about car A right now. Okay. So the car A took 13.33 seconds to reach from 0 velocity to 80 feet per second. Okay. Now, once the car has reached this velocity and we know that how much time it took, okay, we can also find out that how much distance the car traveled in this period. Okay. So we can use the equation number, we can use either equation 8, this is okay, because we know the constant acceleration, now we know the time, and we know the initial velocity as well, and let s not be 0. Okay, or we can directly use equation number 9 as well, both are okay. If somebody use equation 8, somebody use equation 9, both will give the same answer, both are correct. Okay, so s naught is 0, so we can find s. We know the initial velocity is 0, we know what is the final velocity, we know what is the constant acceleration, so we can find that how much distance traveled by car A while it reached the velocity of 80 feet per second starting from 0. So if we just substitute the values, we'll find this distance. Is this thing clear or not, first of all? Okay, now what we need to do is that, remember one thing, car A and car B are moving towards each other. And a time will come when the two cars are going to be at the same location. So the total time traveled by car A would be the same as the total time traveled by car B. Okay, so one car starts moving from 0 velocity, other car was moving at certain velocity, and they both start moving towards each other. The total time traveled by car A and car B will be same, not the distance. We are not talking about the distance. I'm saying the total time traveled by the car A and car B will be the same when they meet each other, okay, or when they pass each other. So let's say that this total time is t1. Let's say that this total time is t1. So when we talk about car A, so initially car A was accelerating. So during the acceleration period, the car A took 13.33 seconds. So the total time traveled by car A will be what? It will be t1. But 13.33 seconds was the time when it was accelerating. The remaining is the time when the car A is not accelerating. Okay, so the remaining time when the car A is not accelerating, that will be t1 minus 13.33. Do you understand this point or not? This is an important point. This is the real catch for this problem. Okay, you have to understand one thing. Car A and car B are moving towards each other. The total time taken by car A will be the same as the total time taken by car B when they pass each other. So let's say this total time is t1. So when we talk about car A initially accelerates and then acceleration is 0. So when the car A is accelerating, that time we calculated is 13.33 seconds. So the remaining time the car A travel is t1, which is the total time, minus 13.33 seconds. Do you understand this thing or not? This point is important. I want to know, do you understand it or not? Please answer me. If anybody don't understand, you can ask me, no problem. Okay. So the time traveled by car A is in two, or the distance traveled by car A is in two portions. In one portion there is acceleration, in another portion there is no acceleration. Okay, so when there is acceleration, we find out that the time taken was 13.33 seconds. So when there is no acceleration, then that time will be total time, which is T1 minus 13.33. So that is the time taken by car A, when there is no acceleration. So remember, when there is no acceleration, which equation can we use? When there is no acceleration means that AC is 0. That is the point when we can use equation number 10 only. So S is equals to V naught T. So this is S2 is Vt, where T will be the time when there is no acceleration, which is T1 minus 13.33. And the velocity is fixed because when it reached 80 feet per second, then it remained at 80 feet per second. That's written in the question. Okay. Written afterward, it maintained this speed. Which is speed? 80 feet per second. Okay. So that becomes the equation for the for the second distance. Okay, so the distance for car A is divided into two parts. One part when there is acceleration, other part when there is no acceleration. When there is acceleration, that distance is known, 533.33 feet. Okay, we calculated it. But when there was no acceleration, we don't know how much is that time. Okay, but we know the equation here. Now let's talk about car B. Now car B is from the beginning moving with a velocity of 60 feet per second, and there is no acceleration. So AC is 0, that means only equation 10 can be used. And equation 10 will be S is equals to Vt, but car B has only one time zone, only one period. Okay, there are no two different regions for car B. Okay, it was same 60 feet per second velocity that has been moving. So the total time traveled, if it is T1, so it will be S is equals to 60 T1. So now we know that initially both the cars were at a distance of 6,000 feet. They were 6,000 feet away from each other. When they meet each other, that means the total distance traveled is 6,000 feet. So that is the distance traveled by car A, which is S1 plus S2, plus car B, which is S3. So distance traveled by car A is S1 is already calculated. S2 is 80 T1 minus 13.33. S3 is 60 T1. Okay, so now we got one equation where T1 is unknown, where we can calculate, we can find what is T1. T1 is the total time. So once we know the total time travel, so we can find what is the distance traveled by car A. Distance traveled by car A is S1 plus S2, where S1 we already calculated, S2 is 80, T1 minus 13.33, that's about 3,200 feet. So with this, we solved this problem. This problem was a bit complicated problem. However, the main catch is the understanding of this point, that the car A travels, the time taken by the travel for car A is the same as the time taken by the travel for car B. And let's say this is T1. So car A travels in two sections. In first section, it is accelerating. In the second section, acceleration is 0. So in the first section, when it is acceleration, time is calculated, it is 13.33. Then the remaining time it used is T1 minus 13.33. This is the main catch. If you understand this thing, the problem is simple. So anything that anybody feel that he is not able to understand, please raise the question, ask. Inshallah, I will be able to answer. Please feel free to ask any question if you want. If there is anything, this is a complicated question. I'm spending time, and I'm willing to explain again if you are not able to understand it. But do you see one thing here? The choice of equation was very important. You see, the first two equations we applied for car A because we know that there is an acceleration in the car which is not 0. So we applied equation 7, 8, 9. Okay, and then when we know that the acceleration is 0, we applied equation 10 here. And for car B, we already know from the beginning acceleration is 0, so we applied only equation 10 here. So which equation has to be applied? This is very important. That's the theoretical background that you should know. Okay. So actually the time is over. From 6 to 8 is the time of the class. So right now it is 8 o'clock. So I'm not going to continue forward. Okay. At this point, I'm going to stop here, but I need to know if you understand it or not, because we spent some time over this question. If you have any problem, it's better you can ask. I can answer you. Otherwise we can finish, because next time when we're going to start, maybe it will take a lot of time if I start explaining the problem again. Is it clear so far? Anybody has any question? Okay, if nobody has any questions, so we are done here today. We are going to continue inshallah next week. I'm going to wait the email of you of the class leader to make sure that what time do they suggest for the class. If anybody has any issue, we can continue with 6 to 8, but if nobody has any issue, 4 to 6 is also an option. Okay, so you are allowed to leave the meeting if you do not have any question, and if it's the class time is over.